Let's talk about chemical bonds. So here's how you can use this video. Throughout this video, there'll be slides that have some text that's highlighted in green. If you're using this to take a notebook, that's like the important key concepts that you should have in your notebook. There's also going to be blue text. These are questions for you to answer or questions for you to consider. Now, also throughout this video, there's going to be two codes, one a verbal code said by myself and one written code that'll pop up on the screen. So they can appear in any order, so keep an eye out. All right, let's get started. So before we talk about bonds, we need to talk about electronegativity. So electronegativity is the power of an atom in a molecule to attract electrons to itself. This is going to help determine what type of bond will form between those atoms. And you can see here the greater difference in the electronegativity between those two atoms, the more polar that bond is going to be, meaning more one-sided, right? Those electrons are going to go to one element or the other. And you can see here off to this, there's a periodic table, and they do have numbers associated with them. The higher the number, the more electronegative it is. Fluorine has the highest with 4.0. And you can see those noble gases, well, they don't want any, right? They're except, I guess, in the one up here. Krypton and xenon, I guess, can bond with some things, but those are special cases. We won't worry about that. But I like this three-dimensional one because it really shows which atoms want those electrons more. And all you do, if you're given two elements, just subtract those, and you'll be able to tell which type of bond it is. Now I'm going to show you a little shortcut that isn't always true, but will help us determine what bond it is really easily. So the first bond we're going to talk about is a covalent bond. So a covalent bond forms when two atoms share electrons, and this occurs mostly between nonmetal atoms. So if I've got two nonmetal atoms that are bonding, they're going to have pretty similar electronegativities. Those are going to be, it's going to be a covalent bond, meaning it shares. That's like the key word there. Those electrons are shared in order to sort of get that octet rule, that full valent shell. Now, something that is special to covalent bonds is that you can have multiple covalent bonds. You can have a single bond, double bond, or even a triple bond. So you can see over here, like this is a great one with this water, H2O. You can see oxygen has 6 valence electrons. Well, it wants 2 to form that octet rule. So it's going to borrow 1 from each of these hydrogens. And that means that, well, oxygen is good. It's got the octet. And hydrogen is good because, remember, the octet rule, well, it doesn't quite apply to hydrogen because hydrogen only has 2 spots for electrons. So that is covalent bonds, shared electrons. Now, there's a special type of covalent bond. This is still a covalent bond, but it's called a polar covalent bond. It's formed when two atoms are still sharing those electrons, but they're unequally. So we have a moderate difference in electronegativity, and this is going to create like sort of a positive side and negative side, slightly positive, slightly negative. Great example of this is going to be water, H2O. So oxygen has a high electronegative number. It's going to pull those electrons a little bit closer to it, so it'll be slightly more negative than those hydrogens, and you've got a slightly positive side, slightly negative side. And this is going to come into play when we talk about a different type of bond later. We'll go over that later. Now, whether it's polar or regular covalent, naming covalent compounds is going to be the same for all of them. The first element is going to keep its full name, and it's usually the less electronegative if found more to the left and lower on that periodic table. The second element, you drop the end of its name and add "ide." And then you use these prefixes. So you can see these prefixes over here. And the only exception that might throw you off is you do not use mono for the first element if there's only one. So here's an example, CO. 1 carbon, 1 oxygen is carbon monoxide. Okay, now I've got CO2, carbon dioxide. Here's N2O, dinitrogen monoxide, and this PCl3, phosphorus trichloride. So really simple. And let's get some practice with naming covalent compounds. So at this time, I'll go ahead and give you that verbal code. The verbal code is 599. Say that again, it's 599. So here are some problems, and I'm not going to go over all of them. But on the left side, you can see here I have some written out. And then on the right side, I have some that are the formula, and you have to give the name. So I'm not going to write out the name just because it takes me a while, but I'm going to go ahead and do a couple. The first one is dinitrogen monoxide. So I'm just going to write first the symbols here, right? So I've got hydrogen and oxygen. Di means two. Oxygen means one, but you don't write the one. That's H2O. That's just water, right? That's the chemical formula for water. I'm going to do this one down here, diphosphorus pentoxide, and just because each of them have a prefix. So I'm going to write those elements out. I've got phosphorus and oxide, which is oxygen. Di means two, and pent means five. Now let's go on to the right side. I'm not going to write them out. I'm just going to say them. Let's see here. I'll start. You know what? I'll start with this one. Right? We've got phosphorus and chlorine. So remember, you don't use mono if it's the first one. So this is just going to be phosphorus trichloride. And then I'm also going to do this one here. Here we go. Right? So this is another phosphorus, but now I've got four of them. This is going to be tetraphosphorus. And then here's oxygen. It's got 10 deca oxide. So very easy, right? And this rule, it's really not tricky at all, right? You just follow the prefixes, just follow those rules. Now, let's move on to Lewis dot structures. So this can be a little bit tricky, and I'm going to walk you through a couple of examples, but Lewis dot structures show how the valence electrons of atoms in a molecule, and here are the steps to drawing them, and you can see some off to the side. The first, to determine the total valence electrons from all the atoms in that molecule. Draw the skeletal structures, so connecting atoms with single bonds, and those count as two. All those lines count as two. Those are those shared electrons. And the least electronegative is in the center, not hydrogen. So hydrogen's never in the center. And then distribute those remaining electrons as lone pairs to complete those octets. On the outer atoms, and remember H has two, right? Hydrogen has two. Place any leftover electrons on the central atom, and then make multiple bonds if the central atom does not have an octet. So remember, covalent bonds, you can have double or even triple bonds. So here is some practice, right? I won't do all of them. You can practice them on your own, but let's just go ahead and do some of them. I'm going to do just a couple of them here, right? Let me go ahead and I'll do H2O, water, right? So the first thing is I got to decide, well, how many valence electrons each of them has. So hydrogen has one, so I have two of them, so hydrogen has two valence electrons, two valence electrons from hydrogen. Oxygen has six. So I add those up, and you're going to have 8 valence electrons. And if you're confused about that, remember, looking at the periodic table, it's just determined by the group number, right? So on the ones that, like 13 through 17, just ignore the 1. So I have 8 valence electrons. Now I need to draw the skeletal structure. So I've got oxygen, I've got hydrogen, and I've got another hydrogen. And what I'm going to do is I am going to connect them. And remember, these represent 2 electrons. Those are the shared ones. So of the 8 electrons, I've already taken care of 2 of them. So I've got, 4 of them, right? 1, 2, 3, 4. So now I distribute them. And it says, and the first step is draw on the outer ones. Hydrogen is good. It already has 2. So then I need to distribute the rest as lone pairs. So there they are, and there they are. So now oxygen, right? Here's my oxygen. It's got 1, 2, 3, 4, those shared, 5, 6, 7, 8, and hydrogen is good with those 2. This is what the Lewis dot structure for H2O is going to look like. So now I'm going to do another one, right? And this one has that last step. So let's do carbon dioxide here, right? So carbon has 4 valence electrons, and I only have 1 carbon. Oxygen has 6, but I have 2 of them, right? So once I do that, let's see here, 6 times 2 is 12. I get 16 valence electrons. Those are the ones that I have to take care of. So here's how I'm going to draw this, right? I've got carbon, and I'm going to connect it with oxygen here and oxygen there. I'm drawing the skeletal structure. So these are I know they're going to be connected. So here are my shared, right? 1, 2, 3, 4. Right, so I already took care of the 4 of the 16. I need 12 left. I'm going to distribute them, making that octet rule. So 1, 2, 3, 4, 5, 6, see here, 7, 8, 9, 10, 11, 12. All right, so that's good. Actually, I probably should, you know what, I'll put the oxygen over here, right? That's where it's really supposed to go. Right, let me just erase that real fast. There we go. So the oxygen's supposed to go over there, right? It's not really that important until you get to, like, you know, which way the charges are going to be. So now with this, my oxygens are good. They have 8, but my carbon, notice, only has 1, 2, 3, 4. Those ones that it shares with oxygen. So in this case, now we need to make some double bonds here. So I'm going to take these two, I'm going to scratch them out, right? And I'm going to make those a bond. So oxygen still has 8. I'm just sharing them with this. Now also notice, well, this carbon has these 2 shared pairs here, 1 shared pair here, so it's got 6. It's still not good. We need to get to 8. So I'll just scratch these 2 out, right? And what I'm going to do is I'm going to make those a double bond. So this is carbon dioxide. It's got those double bonds. And if you want to see what a triple bond looks like, I'll give you a hint. Go ahead and try nitrogen, right? N2, try that yourself. So here are some examples that you can do on your own and to help practice. And you can see here, like especially these here, C2H4, C2H2, those are going to have those multiple bonds that you need to be careful of. So just moving on. Now that's covalent. Now we can sort of stretch out. Now let's talk about ionic bonds. So ionic bonds are formed when one atom transfers electrons to another. So now we're talking about a complete transfer of electrons, not sharing anymore. It occurs mostly between a metal and a non-metal atom. So that's why it's important to distinguish like what's metal and non-metal. That's why I say mostly, because it does get a little tricky. And if you're subtracting it, it's like going to be greater than about like 1.7. Now, this results in the formations of those ions, cations, which are positive, anions, which are negative. And here's an example here, right? And this is the best example. This is just table salts. Sodium, right, gives up its one valence electron. Chlorine takes that one valence electron. Well, sodium becomes positively charged. Chlorine becomes negatively charged. And because I've got a positive and negative, they attract, right? And because we're completely giving up those electrons and taking those electrons, we're not dealing with like multiple bonds. Now, here's how you find out how many of each element you have in each. Because if you're giving them, like, because we're not dealing with like the multiple bond situation, because you're not dealing with it, it does get a little bit tricky because we don't use prefixes. So here's how you do it. It's called the crisscross method, right? It's used to write the chemical formula of an ionic compound. So first you write the symbols, and then you find those charges. Crisscross the charges, so you drop the signs, right? Simplify if needed. So this is to make that neutral ionic compound. So if I'm looking at this one, here's an example too, and I'll just go over an example real fast. Aluminum, oxide, and I'm going to go over some examples after we go over naming, because you have to use a crisscross method. So speaking of naming ionic compounds, it's a little bit trickier than covalent because we're not using prefixes. So here's what you do. First, use the element name for the cation, which is the metal, right? It's just the element. Second, use the root of the anion, metal plus ide, so you drop the end, you add ide, same thing as covalent bonds. Now for transition metals, use Roman numerals to indicate charge. So there's a little additional thing, because those transition metals in like 3 through 12, they can form multiple charged ions. Well, only some of them can, right? You can see there's some examples on this picture here. No, there's no prefixes. You don't use prefixes. That's why it's a little bit tricky. So here's an example, like sodium chloride is one, and then you have like, iron chloride here, right? You're not using prefixes, but notice iron, I have to indicate that it's got that positive 3 or 3 positive charges. So I'm going to just go over the crisscross method here, right? And so here are some examples that you can get. Naming, if you have the formula, is really easy because you're not dealing with any prefixes. You just have to be careful of those charges especially down here, right? So you've got, iron chloride. You have to know that iron in this, the first one, is going to be a charge of 3. So you put the Roman numeral 3 down here. That is going to be 2. Right, so you just have to indicate that. Now, I'm going to help you out with some of these here, right? So we'll do, how about this? I'll do potassium oxide here, right? So first what you need to do is I'm going to write the symbols, right? Potassium, oxygen. Potassium is going to make an ion of just a positive 1 charge, right? Or 1 positive charge, basically, right? Oxygen makes it's 2 negative charges. Now what I mean by the crisscross method is I take the 1 up here, bring it down there, the 2 here, bring it down there, and what I get is, well, potassium, I got 2 potassiums, oxygen, right? And what this does is this makes a neutral ionic compound. That's it. That's really it. Right, that's really it. You just crisscross, and what that does is that, like I said, it makes that neutral compound because potassium only has 1 charge. Well, I have to have 2, so this will get me 2 positive charges, and oxygen has 2 negative charges. I should have put the positive on the other end, right? So these cancel out, and I've got a neutral ionic compound. So that's really it, right? That's just about it. And you can practice the rest here. Now, the last 2 things we need to talk about, these are like special cases. So metallic bonds occurs between metal atoms. Now, metal atoms share a sea of delocalized electrons that move about freely. They don't really belong to, we're not talking about, it's kind of like sharing, but it's not like, hey, I'm sharing with this one other atom. It's, hey, they belong to like everyone. They're sort of free floating. They're centralized. That's why, and you'll see this a lot, the sea of electrons. Now this gives those metals their properties like conductivity and malleability. So they're very conductive to heat and electricity because those electrons can free flow freely. So example would be like copper, right? They share electrons in a metallic bond. So basically, if you're looking at those like transition metals, these are very great examples of those metallic bonds. Now, the last thing that we need to talk about is hydrogen bonding. It's not a type of connecting like atoms together to form a different compound. Hydrogen bonding is a type of intermolecular forces, so in between different molecules, where hydrogen atom is attracted to an oxygen, nitrogen, or fluorine atom in a nearby molecule. It occurs when, yeah, and that sort of says the same thing. So here's what it is, right? So, and water is really the best example of this. So what happens is, we already talked about this with a polar bond. Because oxygen wants those electrons more, it becomes slightly more negative than those hydrogens, right? Those positively charged, right? Positively charged ions right there, right? They're not ions, sorry, they're not ions, but they're positively charged part of this covalent compound. Now, because I've got a positive and a negative, I'm going to get a slight attraction here, right? It's not like a complete bond, but I like to think of it, and what I've heard before is like it's like a stickiness, like these molecules stick together, and this is what causes surface tension. This is why if you see droplets, like that's what keeps that, like the surface tension, right, so strong, is because of these hydrogen bonds. It's also the reason why plants can get water, up like a large like tree trunk, right? It's because of those slightly positive and negative poles to the water atom. So that's hydrogen bonding. Special case, right? But yeah, it's just a type of bonding there. So just as a final thought, remember there's too much unknown in the universe to take a break from learning. Get out there and question everything.